So the next talk will be given by Satoshi Kura, who will tell us about the hierarchy of supermartingales for omega regular verification.
All right. Thank you for the introduction. Right. So in this talk, we consider the verification of omega regular properties of probabilistic programs. So concretely, suppose that we are given Markov chain together with an omega regular specification over its traces. So here, the Markov chain represents a probabilistic program. So its state space may be infinite in general. And moreover, we consider a specification expressed as either a Streett or parity condition. And our goal is to determine whether the Markov chain satisfies the omega regular specification with probability 1. So here's an example. So this program repeatedly runs a biased random walk while incrementing the initial position. And in this setting, one question we may ask is whether the location L1 is visited finitely often with probability 1. Another question is whether L0 is visited infinitely often with probability 1. These are typical examples of qualitative omega regular verification problem. And in general, omega regular specifications are expressed using Streett conditions, which are finite conjunctions of Streett pairs. Since a finite conjunction of Streett pairs can be handled component-wise, we focus on a single Streett pair without loss of generality. And formally, a Streett pair for Markov chain is defined as a pair of subsets of its state space. And a run of the Markov chain satisfies the Streett condition if either A is visited finitely often or B is visited infinitely often. And there's an existing work on this problem. Streett supermartingales are an existing technique for verifying omega regular properties. And they can be viewed as a generalization of ranking supermartingales where the ranking condition is adapted to a Streett pair. So formally, a Streett supermartingale is defined as a non-negative function that satisfies these three conditions. So if the current position belongs to A, then the expected value of R in the next step decreases by at least 1. If the current position is in B, then R may increase in expectation, but by at most M, where M is a fixed constant. And if X does not belong neither A nor B, then R must be non-increasing in expectation. So this is the definition of Streett supermartingales. And the existence of a Streett supermartingale guarantees almost sure satisfaction of the Streett condition. Intuitively, if the Streett condition were violated, then states in A would continue to occur, but states in B eventually disappears. So by the ranking condition, the value of Streett supermartingale continues to decrease, and which eventually violates the non-negativity condition. So this is the intuition of the soundness. So now, let's consider how powerful are Streett supermartingales. Unfortunately, Streett supermartingales cannot verify the simple example shown here. In this program, this program is a simplified version of the various repeated random walk that I showed earlier. But here, the current position M is deterministically decremented. And in this case, the Streett condition is satisfied almost surely, but there's no Streett supermartingale. Intuitively, this is because in this case, we cannot satisfy both the ranking condition and non-negativity condition as shown in this picture. So to give more powerful proof techniques, we introduced several new supermartingales for omega regular verification. And also, we study the relationship between these new notions and the existing one. And also, we show some completeness result for our new supermartingales. And then, we implement automated synthesis algorithms and evaluated the advantages of our new supermartingales. Okay, so this slide summarizes the hierarchy of the different notions of supermartingales, and in the middle column, this is the hierarchy for supermartingales for Streett conditions. The bottom one is the existing one, and the other three are new notions. And these four notions are ordered in this way, and each inclusion relation is strict. And among these notions, generalized Streett supermartingales are complete for positive recurrent problems, and distribution varied Streett supermartingales are complete for null recurrent problems. And also, we additionally introduce supermartingales for parity conditions, which is shown on the right-hand side. Okay, so from now, I'm going to introduce these notions. So let me first introduce the notion of generalized Streett supermartingales, or GSSM. The definition of GSSMs is almost identical to Streett supermartingales, but we dropped the condition for B. And so this relaxes the definition of Streett supermartingales. But despite this relaxation, GSSMs remains sound, and its existence guarantees almost sure satisfaction of a Streett condition. And moreover, GSSMs are strictly more powerful than Streett supermartingales. This is because they can verify the counterexample for Streett supermartingales that I showed earlier. Because we relaxed the condition for we relaxed the ranking condition. Next, I will explain the competence result for a generalized Streett supermartingale. So, given a Streett pair, we call a Markov chain positive recurrent if the expected number of A steps until reaching B is finite. And also, we call a Markov chain null recurrent if the number of A steps until reaching B is finite almost surely. So So the relationship between null recurrence and positive recurrence is analogous to the relationship between almost sure termination and positive almost sure termination. And we showed that GSSMs are complete for positive recurrence. This is a consequence of the fact that this is a consequence of the least fixed point characterization of the expected number of steps. But I'm not going into details here. Okay, next, I will explain how we can go beyond a positive recurrence. So I'm going to introduce two notions of supermartingales. Here, we borrow ideas from verification of almost sure termination. So in this setting, more powerful supermartingales can be obtained by replacing the code domain of ranking supermartingales. For example, there's a notion of lexicographic ranking supermartingales, and lexicographic ranking supermartingales use the lexicographic order on tuples of non-negative reals. And similarly, distribution varied ranking supermartingales use the stochastic order on distributions over natural numbers. And this extension makes it possible to go beyond positive almost sure termination. So we use the same idea to omega regular verification. We define a lexicographic generalized Streett supermartingale using lexicographic orders, and we define a distribution varied Streett supermartingale using the stochastic order. The formal definition of LexGSSMs is almost the same as that of GSSMs, but here we use the strict and non-strict lexicographic orders in the ranking condition. That's the main difference. And similarly, we define a DVSSM using the stochastic order in the ranking condition. Then we can show that these two notions are also sound for omega regular verification. And moreover, we showed that DVSSMs are also complete for null recurrence. So this implies that DVSSMs are the most powerful supermartingale in our hierarchy. But however, they have a drawback, which is at present we do not have an automated synthesis algorithm for DVSSMs. And in our paper, we also present examples that separate 3 different classes of supermartingales. So this implies that the inclusion relation between these notions are strict. But I'm not going to explain details. So okay. Next, I will explain supermartingales for parity conditions just briefly. So, it is known that parity conditions are equivalent to Streett conditions, and also, in the case of non-deterministic systems, progress measures are a standard technique for proving, verifying parity conditions. So we combine the ideas of progress measures with Markov chains and obtained a new kind of supermartingales shown here. And yeah, we do not explain formal definition, but we showed that LexPMSMs are as powerful as LexGSSMs. This is proved by constructing mutual translations. And this mutual translation suggests that LexPMSMs are not just as powerful, but also practically has advantage because LexPMSMs often give a smaller certificate. Right. Okay. Finally, I briefly explain our implementation and experiment. So our implementation is based on a template-based synthesis. So we assume that program variables are real valued and use a polynomial template for supermartingales. Then we generate a constraint and solve them to synthesize a supermartingale. For lexicographic supermartingales, we additionally extend an existing algorithm to automatically determine the number of lexicographic components. And this is the experimental result. So this result shows that, so these results are consistent with the theoretical hierarchy. And and also we can see that LexPMSMs are in practice performs better than LexGSSMs. Okay, so that's it for my talk. Last comment, sorry. So our implementation is available online. So if you scan this code, you can find it. Okay, that's it. Thank you for your attention.
Any questions? All right, I have a few. Excellent work. I really liked your talk.
Thank
you. So I have a question about, so for probability one reachability in lexicographic ranking supermartingales, there are works that considered relaxing the non-negativity conditions of some components.
Yes.
Have you considered this for LexGSSMs?
I think the answer is I haven't yet, but I think that's an interesting direction for future work. Yeah.
Okay, I have one more question. So in your completeness guarantees for positive recurrence and null recurrence, do you also assume the supporting invariant, which basically captures reachable states? Is this assumed to be a part of the certificate, or?
We don't explicitly handle invariants in our theorem, but it's relatively simple to combine invariants in our framework, and so roughly speaking.
So maybe to clarify my question. So I mean, for completeness guarantees. For the certificate to be complete, I mean, the defining conditions usually need to be restricted only to reachable states. So are you assuming that basically you have the set of reachable states or some sort of invariant which captures it?
Maybe there's some so completeness. So well. So in our problem setting, we consider actually I didn't explain very explicitly, but our problem is to show that omega regular specification. So show that the Markov chain satisfies omega regular specification for any initial position. So.
Oh, I see. I see. Have you then considered a variant when you're given an initial set? Would something change? I guess soundness will still hold, but what about completeness?
I'm not sure. What would be the statement for competence in that case?
Okay, maybe we can discuss offline.
Maybe you can talk offline.
All right, let's thank the speaker again.